covariance estimation. It's a joint work with Rong, Elias, and David. So this is a 10 seconds version of the problem we're studying in this paper. So we want to estimate the covariance of a distribution from samples, except there's one catch. So there's an adversary that can change a small fraction of the samples. Right? So now let me define this more formally, starting with the version without corruption. So this is covariance estimation 101. So you're given n samples drawn from a d-dimensional Gaussian, and your goal is to estimate the unknown covariance sigma from these samples. All right, this is a very well-studied problem. So we know this empirical matrix works, and we know how many samples we need to take for the estimate to be within epsilon close to the truth. I would like to note the running time of this algorithm in computing this matrix. So the input size here is roughly d cubed. And you can compute this matrix through fast rectangular matrix multiplication. And that takes time roughly d to the 3.26. Okay. All right, so now an adversary shows up. And this is formally the model we consider in the paper. So the algorithm first specifies a sample complexity n, and then n samples are drawn from this true distribution, in this case Gaussian. And the adversary looks at everything, the sample, the ground truth, and the algorithm. Okay, and then it changes 1% of the samples. And the goal is to robustly estimate the covariance given this corrupted set of samples. All right, so what's known about this problem? The mic is out of batteries. All right, so what's known about this problem? So a recent work gave polynomial time algorithm that computes either dimension independent or near independent error. But however, if you look at these algorithms more carefully, you will see that they run, this is their running time, and this has a gap between these algorithms and the runtime of the best non-robust algorithm, which is just to compute the empirical covariance. Okay, so the main contribution of our work is to close this gap. More broadly, we're interested in the following question. So we want to design robust statistical estimators that runs as fast as the non-robust ones. The answer to this question was shown to be yes for robust mean estimation in an earlier work by a subset of authors. Without further ado, this is our main result. So we showed that we gave two algorithms, both run in time d to the 3.26 when epsilon is a constant, ignoring polylog factors. So the first line is a multiplicative guarantee. It implies the additive guarantee on the second line, but you do need to pay a log condition number in the running time. We also give some evidence of suggesting improving our running time might be hard. Okay, so this matches the running time of computing the empirical covariance matrix. Right, so in the remaining 5 minutes, I'm gonna get a bit more technical and try to show you some of the main ideas of this work. So first, let's take a look at the most naive approach. So when X is drawn from a Gaussian with mean zero and covariance sigma, the expectation of XX transpose is just the covariance matrix we're trying to estimate. Okay. So this, roughly speaking, this gives you a reduction that you can just reduce our problem to robustly estimating the mean of Z instead, where Z is the tensor product of X with itself. It's a D square dimension vector. Right, however, there are many issues with this approach. The most obvious one is it's too slow. It actually would take time roughly d to the 4 to just write down all the input, because you have n, which is d square samples, and each of them are d square dimensional. Okay, so the challenges we face in this work, the one is, as I said earlier, we basically want to estimate the mean of this d square dimensional distribution without actually writing out the samples explicitly. Okay, there's another issue That is, robust mean estimation algorithms. This problem, robust mean estimation, requires some assumption on the covariance matrix. But in our case, the covariance of x O times x corresponds to the force moment of our Gaussian, but we did not make any assumptions on the Gaussian. So due to time constraint, I'll only be able to tell you about how we address challenge 1. And to do that, I'll first recall the approach in the earlier work for robust mean estimation. So the key step in that algorithm is to solve the following problem, is the following observation. So when you have no corruptions, if you are trying to estimate the mean of a distribution, what you should do is you just find the direction that maximizes variance of the projected samples. So in this case, you will find this direction y, and you can show that y would roughly point to the true mean. Okay. However, this is no longer true when you have corruptions, because this direction y prime might have larger covariance than y. Okay. It turns out the right thing to do is to, after you projected samples along this direction, you remove the 1%, remove the epsilon fraction that's farthest away, and then use the remaining, the variance of the remaining samples as your measure, okay? If you do this, you will recover the direction y again, even in the presence of corruptions, okay? It turns out you can cast this as a positive SDP, so the bottleneck of the algorithm is just to solve these positive SDPs logarithmic number of times. Okay, so what we do in this paper is to come up with a faster solver for these SDPs when the input has certain structure, namely they're tensored with themselves. So this is a standard pair of packing covering SDPs. And here AI is the ZI transpose, and ZI are the tensored outcomes. So note that we're not writing down AIs, and we're not even writing down the ZIs. Okay, but nevertheless, in this paper, we show that you can exploit the structure of these AIs and solve this problem very efficiently, essentially in the desired matrix multiplication time. All right, so now let me move on to hardness results. So it is not known, even when there are no corruptions, we do not know how to compute an empirical covariance matrix faster than this matrix multiplication time. And in this paper, we gave a communication complexity lower bound that shows you any oblivious sketching algorithm will not help you for this problem. So I don't know how to do this faster. One other question is you could propose a weaker version of the problem where you say that you don't have to output the matrix, right? Just give me a set of good weights and make the weighted empirical matrix close to the true covariance. Okay, so in this case, if there's no corruption, the problem is super easy. You just output the uniform weight. Okay, and in the paper, we showed that even for this easier version of the problem, if you want to solve the robust version, you still need to solve some basic matrix computation problem where all existing algorithms need to do d squared d matrix multiplication. Okay, so and finally, open problems. I think at the higher level, the most important open problems are still to answer this question for a larger family of problems. The mean and covariance estimation are resolved, but there are many problems that's still open. And in terms of immediate technical questions, you could ask to remove the dependency on the condition number, or epsilon, in the running time of our algorithm. And I want to say that very recently, there are 2 papers that remove this epsilon dependency for robust mean estimation, and we believe the same algorithmic technique would apply to covariance estimation as well. All right, and that's it. Thanks. So I think it's necessary with a SQ algorithm. Yeah, there's a SQ lower bound for it, but that's it.
Let's thank the speaker again. So our next talk will be by Dylan Foster on a paper by him and Vasilik Serganis. This paper has won the Best Paper Award, so please join me in congratulating the authors.
Wait, is the clicker around here? You want a clicker? Yeah, I'll take it. Cool. All right, thanks. Yeah, so this is about statistical learning with a nuisance component. And our problem is sort of motivated by the fact that, in the last few years, machine learning has come to play a larger and larger role in like decision-making problems. And these are two different types of problems that have different goals. So, in machine learning, we're usually interested in, making predictions from data. Like does an image contain a cat or a dog? And, in decision making, we're kind of more interested in like counterfactual inferences. Like maybe I have a data set where one action was made. What would have changed if I had made a different action? So these are kind of two different goals, but there's a growing body of work that shows that, machine learning can be useful for these counterfactual inference tasks. It's just that we need to do additional work on top to sort of debias the predictions that come out of machine learning. So the goal of this work is to sort of unify all these efforts under the blanket of statistical learning and give general tools for using statistical learning to solve counterfactual inference problems. And the key tool we're going to use to do this is what's called nuisance parameters. So the idea of using nuisance parameters to debias our predictions. So to make this a little bit more concrete, I'll focus on the problem of policy learning, or sort of like an observational version of contextual bandits. So this is a setting where we're going to get n triples of features, binary treatments or actions, which are called T, and rewards, IID. And for each example, we only see the reward of the treatment that was taken, not the treatment that was not taken. So if the treatment that was taken was 1, we just see the reward of treatment 1. And our goal is to find a policy that maximizes the expected reward under this distribution. The challenge is just that because I only saw the reward for the treatment that was taken, I can't just evaluate the sample version of this objective.